Dear students, this is my second lecture on waveguides. In the last lecture, that is in lecture 1, we have seen what is a waveguide and the differences and the similarities between the waveguides, which are high frequency transmission lines, with the low frequency transmission lines like two conductor transmission lines and the coaxial cables. Okay, in this lecture, I'm going to tell you about what is electromagnetic spectrum and different band designations, and also the classification of rectangular waveguides. But before we proceed to that, I would like to first tell you what I'll just try to give you what is the complete syllabus that we are going to complete in these 20 or maybe 22 lectures. Okay, so first I would like to cover electromagnetic spectrum and bands, and next rectangular waveguides means classification and what are the various modes which are possible in that, and the next solution of wave equations in rectangular waveguides, and next transverse electric and transverse magnetic mode of analysis. Then we will find out the expressions for the fields and characteristic equation and the expression for cutoff frequencies. In the expression of fields, we'll first find out Ex, Ey, Hx, Hy, the field components in terms of Ez and Hz. Why? Because we'll consider the wave is propagating initially in Z direction. And after finding out the cutoff frequency, we'll try to see the dominant and degenerative modes in both the mode of propagation. Then we'll see the sketches of a few of the transverse electric and transverse magnetic modes. Then we'll see phase and group velocities, then wavelengths and impedance relations, and finally equation of power transmission lines and impossibility of transverse electromagnetic mode, why this mode will not exist in waveguides, and microstrip lines and Z0 relations. Okay, so these are all the topics that we are going to cover in these maybe 20 to 25 lectures. Okay, now I'll be moving on to the electromagnetic spectrum and bands. So this is what we are going to see now. What actually this electromagnetic spectrum is? Maybe you might have seen this in your 11th and 12th standard a little bit. Okay, but first let us try to define what is this electromagnetic spectrum. This electromagnetic spectrum actually means the band of frequencies or wavelengths, in which the electromagnetic radiation extends. That means maybe the frequency which is starting is 1 hertz, and the highest frequency can be extended to 10 power 25 hertz also. Okay, that is maybe more than exahertz. Okay, so it's 10 power 3 can be generally called as kilo, 10 power 6 is mega, 10 power 9 is giga, 10 power 12 is tera, 10 power 15 is peta, and 10 power 18 is exa. Okay, as far as the microwaves are concerned, will be generally take up to 10 power 18, which we call it exa. Okay, now after seeing this electromagnetic spectrum, okay, we'll now just moving on to the different types of band designations which are given by the various industry standards. Okay, so here this standard is this particular band is given by CCIR, that is Consultative Committee for International Radio, and this is given the band designations, and this is the most important band designation which is given. Okay, so this table is given as, okay, first column we will be seeing the band number, and in the second column we are having the frequency range, and the band name or band designation is given in the third column. Okay, that is here. Okay, right. So now we'll try to see the first band. Generally the frequency range will be given in terms of multiples of 3, and which is starting from 3 hertz to 30 hertz. The general gap is, okay, that is 3 hertz to 30 hertz, which we call it as ultra low frequencies, which is called as ultra low. ULF means ultra low frequencies. And second is 30 hertz to 300 hertz, we call it as extra low frequency, 30 hertz to 300 hertz. And next, 300 hertz to 3000 hertz, or we can call it as 3 kilohertz, which we are calling here as voice frequency. Generally, our voice frequency will be 20 hertz to 20 kilo, which will be in that. Okay, and the next 3 kilohertz to 30 kilohertz is very low frequency, very low frequency. And next we'll be moving on to 30 kilohertz to 300 kilohertz, which we call it as low frequency. Then 300 kilohertz to 3000 kilo or 3 megahertz is called medium frequency. This entire table is very important, that's the reason I'm concentrating more on it. And 3 megahertz to 30 megahertz is called high frequency, and 30 mega to 300 mega is called very high frequencies. This is very important question asked so many times in competitive exams. And 300 megahertz to 3000 or 3 giga is called ultra high frequency. Then 3 gigahertz to 30 giga is called super high frequency, and 30 giga to 300 giga is called extreme high frequency, extreme high frequency. And then 300 gigahertz to 300 terahertz. Okay, so 3000 giga is called 3 tera, and 3 tera to 30 tera, and 30 tera to 300 tera. Overall we are calling it as infrared light, IR. Okay, IR light we call it. And then we will have 300 terahertz to 3 peta. Peta means 10 power 15, and which we call it as visible light. And 3 peta to 30 peta we call it as ultraviolet light. And 30 peta to 300 peta is called X-rays. Everybody has to remember this. And 300 peta to 3 exa. Exa means 10 power 18, and 3 exa to 30 exa are called cosmic rays. Okay, so the CCIR has given up to 30 exa, but maybe we'll have further, which will be further calling it as cosmic rays only. Okay, this is the band table which is given by the CCIR. Next we'll be having one more industry standard which is given by the IEEE people, and in this we have the band designation names and frequency range, which will be mostly expressed in gigahertz, and we'll be starting with ultra high frequency range to G, and lastly R. Okay, so everybody has to remember at least up to this. Okay, so that means UHF range is generally from 0.3 to 3 gigahertz. L frequency range is 1.1 to 1.7. LS frequency range is from 1.7 to 2.6. S frequency range is 2.6 to 3.9 gigahertz. C band is 3.9 to 8, and this is a very important band. Generally you will see this in microwave. Most of our microwave devices will be operated at X band frequency range, which is 8 gigahertz to 12.5 gigahertz or 12 gigahertz. All the microwave bench setups will be working in that particular frequency range, and a little bit further frequency we call it as KU, which is also important in competitive exams. And K band of frequency is 18 to 26, and KA is 26 to 40. Okay, so these are all the frequency bands which you have to remember and which is given by the industry standard. And then we'll be moving on to this IEEE. Here stands for Institute of Electrical and Electronics Engineering. Then we'll be moving on to the different types of waveguides. Okay, so what are the waveguides, different shapes that are available for us, and on which particular waveguide we'll be concentrating more, and what is the waveguide which we have in our syllabus. Any shape of cross section of a waveguide, any shape of cross section of a waveguide can support electromagnetic waves. That means whatever is the shape that you take, Okay, the electromagnetic wave which will generally propagate through that. So that's the reason waveguide can take or may take any particular shape. In that, few will be here we are taking. So the waveguides are classified as, the first one is a rectangular waveguide because the shape looks like a rectangle. And second is circular waveguide. Here the front view of the circular waveguide will be like a circle. Elliptical waveguide, it is the front view of the elliptical waveguide will just look like an ellipse. And next we have single rigid waveguide, and we also have double rigid. Rigid means just like a twisted waveguide, okay, which can take any shape. Okay, so these are all the 5 waveguides which are available, but among these 5, okay, these are the 2 most important, and this particular rectangular waveguide will be concentrating almost more than 90%. Okay, so here we'll try to see the shapes of these waveguides. The first waveguide is a rectangular waveguide. As I said earlier, the shape of this is like a rectangle. You can observe this. Okay, and this is the length A, which we call it as width of the waveguide. Okay, which will be generally expressed in centimeters. And this we are calling it as breadth of the waveguide. Generally, A will be greater than B most of the times, and sometimes some people can even design B is greater than A. That shape will be slightly modified here, but 99% of the cases A will be greater than B. A is width here and B is breadth there. So we'll be mostly talking about this particular rectangular waveguide. Now if you look at the other waveguide, which we call it as circular waveguide, which is shown here, it is basically like a cylinder, even though this is not mentioned. So it is like a cylindrical structure. Only the front view will be looking like a circle. Okay, but it is basically a cylindrical structure. And we don't talk much about this circular waveguides. Okay, because previously it was there in the syllabus, but now it is not there. And then we'll talk about elliptical waveguide. This is also not a part of our syllabus, but the shape will look like a ellipse, and this is also of cylindrical structure, but the front view will be just looking like an ellipse. Then we'll be moving on to the single rigid. Okay, the shape of single rigid will be like this, and this is the shape of a double rigid waveguide. Here I am taking a shape like H, but you can have all the different alphabetical order shapes of the rectangular waveguides. Okay, so these are the 5 different types of waveguides which we talk about. But in this, rectangular and circular waveguides are the very famous waveguides and which we use it in general. And circular waveguides tend to twist the waves as they travel through them. Okay, so because the waveguide shape itself is like a circle, and once the wave enters into it, sometimes the waves will be twisted and will be propagating through them. The circular waveguides are used with rotating antennas as in radar. So the main application of circular waveguides is in radars. Radar means radio detection and ranging. So elliptical shape is often preferred in flexible waveguides. Okay, so whenever the flexibility of the waveguide is required, we go for elliptical waveguide. And also the rigid waveguides will also be sometimes convenient, okay, in reducing the waveguide dimensions and where the critical wavelength increasing is required. Okay, so I'll tell you about critical wavelength, which will be obtaining from critical frequency. Okay, what is the relation and all will be studying in the future classes. However, the presence of ridge has the disadvantage of increased attenuation and reduced power handling capacity. So because of the reduced power handling capacity and increased attenuation, we generally don't prefer these rigid waveguides. And that's it about this particular topic. And in the next class, we will be seeing about the rectangular waveguides and its analysis.